So after studying the different configurations like CB and CE, CC is not included for your syllabus. So we will do a brief comparisons between the transistor configurations. So here you can see uh, very first parameter that will be discussing, that is common terminal between the input and output side. So which terminal is made common? In case of CB, as we know that base is made common, and in case of C, emitter is made common, and in case of CC, collector terminal is made common between the input and output side. So the next parameter is input current. So input current in case of CB is IE, and in case of C, that is base current IB, and in case of CC, the base current IB again. And the next parameter is output current. IC will be the output current, collector current will be the output current in CB. Again, the collector current will be the output current in case of C, but in case of CC, IV will be the output current. Next, the current amplification factor, or you can say current gain. So as we know that, so the current amplification factor in case of CB is known as alpha, and it is given by the ratio of collector current to the emitter current. And in case of C, the current amplification factor is referred as beta, and it is given by IC divided by IB. And in case of CC configuration, it is the current amplification factor is referred as gamma, and it is given by the ratio of IE divided by IB. Next, the input voltage, that is next parameter is the input voltage, where we actually apply the input. So based on between which terminals you apply the input voltage based on that one. So in case of CB, between emitter and base terminal, input is given, that's why it is VEB, and this is VB, and in case of CC it is VBC. Output voltage, so where actually you are getting the output. So other nodadadra, in case of CB it is VCB, in case of CE it is VCE, and in case of CC this is VBC. Okay, next, these are the this is very important factor, voltage gain. So voltage gain is medium here, is again it is medium here, and it is less than 1 here. So few more parameters have not listed here, are not listed. So one more factor, one more parameter is current gain. Current gain is high in case of CB as well as C compared to that of CC. So regarding the power gain is somewhat less in case of CB, but whereas it is more in case of C configuration. Next, the two are the input and output resistance. It is very low here, and it is low here, and it is very high here. And output resistance is very high, and it is high here, and it is low here. Applications, so it can be in case of CB, it can be used as a preamplifier, and it is used for the used in the audio amplifier, and this configuration can be used for impedance matching. So next, the we will discuss the two major applications of the transistor. One is nothing but switch, another one is nothing but amplifier. So not operate the transistor as a switch, or not use the transistor as a switch. The transistor must be operated between two regions. One is known as the saturation region, another one is known as and cutoff region. So if you operate the transistor within the saturation and cutoff region, you can use it as an on-off switch. So whenever the transistor is operated in saturation region, means the junctions, the emitter to base junction as well as the collector to base junctions, if these two junctions are forward biased, the transistor can be operated in saturation region. And for cutoff region, you should operate the transistor in such a way that the both junctions, that is emitter to base junction as well as the collector to base junction, both should be reverse biased. So if you operate the transistor in saturation region, it can act like a on switch, and if you operate the transistor in cutoff region, it can act like off switch. You can see here. So here I am measuring this is an CE configuration. You can see I can divide it into two parts. So this is a CE configuration. So here initially I won't be providing any input. Yadu input kodtilla. So if I am not providing any input in case of C configuration, as you know that IB is the base current. If you are not providing, and remember, transistor is a current control device. Current control device in the sense the output current in case of transistor is controlled by the presence and absence of the input current. So that's why it is also referred as current controlled device. Let's say if I am not applying any input here, obviously IB value will be equal to 0. So if IB value is equal to 0, obviously, so since we are expecting an output current IC, which will also will be equal to 0, because as we know that the current amplification factor beta is nothing but the ratio of IC divided by IB, or you can also write it as IC will be equal to beta times IB, beta times IB. But as per according to this equation, since IB is equal to 0, since I have not applied any input here, so input current is 0 here. So if you substitute IB value as 0 here, IC will also turn to be 0. Means, so output current also will be 0, and it can act like a open switch. Open switch. And regarding the close switch, you can see here. So here I have applied an input here. 5 volt input anta na apply ಮಾಡಿರ್ತೀನಿ. So since I have applied input here, you are getting a positive value of IB value here. Since you are getting a positive value of IB, so again from the current amplification factor definition, IC can be written as IC equal to beta times IB. Beta times IB. So since we are applying a small input here, we are getting a positive value of IB. So since if you substitute a positive value of IB, IC also will be positive value, and it is amplified version of IB here, because beta value typically it ranges from 2 to 500. Let us consider the beta value as 10 here. So let's say IB value is 5 microampere, means the IC value will be 10 into 5 microamperes, that is 50 microampere will come into play. So here if you apply a 5 voltage as an input here, then the current can flow from IC to, sorry, current can flow from, conventional current direction will be from collector to emitter, collector to emitter, and I can say now it acts like a closed switch. Closed switch in the sense, this is, I can say, switch is in the on position, and here I can say the switch is in off position. So here the transistor is made acted in the cutoff region, and here it is made acted in the saturation region. I can refer, that's why I can use as transistor as a switch. Here the presence and absence of the IB current, that makes the difference. The very next important application of transistor is an amplifier. So here you can see here, this is again the transistor is pretty very much operated in the C configuration to get its application as an amplifier. You can operate the transistor in CB also, but you won't get the this much efficient output as in case of C configuration. So why this is because, so if you compare the CB and C configuration, the current gain, the voltage gain, as well as the power gain are very high compared to CB configuration. As well as in case of common emitter, the input resistance is very high, as well as the output resistance is very small. These all factors made the common emitter configuration suitable to get the uh, advantage of transistor being used as an amplifier. You can use it as in the CB configuration also, but you won't get the larger output. What is an amplifier? So amplifier anta nododadra, obviously amplifier is a circuit which is going to strengthen the weak signal, or it is going to amplify the weak signal. So here, here I can say the transistor is operated in the C mode here. So since the emitter is made common between the input and output, and this is the base terminal, this is the collector terminal, and this is the emitter terminal. This is an NPN transistor. So here the base terminal, that is P type, is connected to positive terminal of the battery source, and N type is connected to negative terminal of the battery source. I can refer this, I can say the emitter to base junction is forward biased. Okay, and again the collector to base junction, it should be reverse biased, since in order to employ the transistor, or in order to use the transistor as an amplifier, we should act the transistor, or should make the transistor to be operated in the active region. For active region, as you already know that the emitter to base junction should be forward bias and the collector to base junction should be reverse bias. So as we know that the emitter to base junction here it is forward biased, and regarding the collector to base junction, the collector is connected, collector which is again a n-type material is connected to positive terminal of the battery here, and the base is again connected to the positive terminal of the battery here. Remember, the collector terminal is more positive compared to the base terminal. Both are connected to positive terminals only, but this voltage, this battery is of smaller capacity than this battery, or I can say the collector terminal is more positive compared to the base terminal. I can say the collector to base junction is also, now it is also reverse bias. So since these two junctions are biased in such a way that it is operated in the active region, I can use the transistor as an amplifier here. Okay. Okay. Here the magnitude of this input signal voltage is such that it always forward bias the emitter to base junction. This emitter to base junction is always forward biased. So irrespective of the polarity of the signal, means in AC signal you can get the two polarities, positive as well as negative, half cycles. So I can refer this junction as a diode. So I can refer the emitter to base junction as diode. Okay. So the VBB is larger enough. So that if there is any change in the polarity is observed in the case of AC signal, that doesn't make any difference. In the sense, so this emitter to base junction is always forward biased. Let's say if there is a positive signal comes here, means so this diode is more forward biased, means more forward voltage is given. If the negative half cycle comes here, means this diode is less forward biased. I am referring a word, ಇಲ್ಲಿ ಫಾರ್ವರ್ಡ್ ಬಯಾಸ್ ಅನ್ನೋದು ವರ್ಡ್ ನಾ ಹೇಳ್ತಿರ್ತೇನೆ. ಏನಪ್ಪಾ ಅಂದ್ರೆ ಈ ಸಿಗ್ನಲ್ದು ಪಾಸಿಟಿವ್ ಬಂದಾಗ ಜಾಸ್ತಿ ವೋಲ್ಟೇಜ್ ಕೊಟ್ಟಂಗಾಯ್ತು ಈ ಡಯೋಡ್ಗೆ ಫಾರ್ವರ್ಡ್ ವೋಲ್ಟೇಜು, ನೆಗೆಟಿವ್ ಬಂದಾಗ ಕಡಿಮೆ ವೋಲ್ಟೇಜ್ ಕೊಟ್ಟಂಗಾಯ್ತು. ಅಂದ್ರೆ ಅದರ ಅರ್ಥ ಏನು, ಸೊ ಇಲ್ಲಿ ಪಾಸಿಟಿವ್ ಸಿಗ್ನಲ್ ಬರಲಿ ಅಥವಾ ನೆಗೆಟಿವ್ ಹಾಫ್ ಸೈಕಲ್ ಬರಲಿ ಅಥವಾ ಪಾಸಿಟಿವ್ ಹಾಫ್ ಸೈಕಲ್ ಬರಲಿ, ಯಾವ್ದು ಬೇಕಾದ ಪೊಲಾರಿಟಿ ಬರಲಿ, ಈ ಡಯೋಡು emitter to base junction diode, it will remain in the forward bias condition. So since it is forward biased and this is reverse bias, so ಇಲ್ಲಿ forward bias ಯಾವಾಗಲೂ forward bias ಆಗೈತೆ ಅಂತಂದ್ರೆ ಅದರ obviously IC current will flow from collector to emitter. Let's consider the first case. So first case ಒಳಗೆ ಏನಾಯ್ತು, we don't apply any AC current. If you don't apply any AC current, in the sense the AC current ಏನು ಅಪ್ಲೈ ಮಾಡ್ತಿಲ್ಲ ಅಂದ್ರೆ it will be zero. Okay, at zero voltage of AC signal, obviously as I already told you, VBB is larger enough to make this diode in the forward bias condition irrespective of the signal magnitude value here. Let's say it is 0 here, it is 0 idru kuda this is forward biased and you will get a collector current value IC. That current value is referred as zero signal current. ಆ ಕರೆಂಟಿಗೆ ಏನಂತ ಕರಿತೀವಿ, ಜೀರೋ ಸಿಗ್ನಲ್ ಕರೆಂಟ್. ಅಂದ್ರೆ ಇದರ ಅರ್ಥ we don't apply any AC signal here. AC signal ಏನು ಕೂಡ, there is a zero AC signal, at that time also you will be getting an output current IC and this is referred as zero signal current. Let's consider the second case. In case of second case, let's say the inputs, whenever input AC signal is applied during positive half cycle of the input signal, during positive half cycle of the input signal, the forward bias across the diode or across the emitter to base junction, it is increased. So this increases the collector current also. That is IC. The increase in the collector current produces a large voltage across the RC. So since we are measuring the output at the RC here, so V0, so if you are designating it as V0 will be nothing but IC into RC. RC is constant here. Since IC is getting varied according to the signal here, since we have a positive half cycle here, with positive half cycle this emitter to base junction is more forward bias ಆಗಿರೋದ್ರಿಂದ IC also will increase. So IC is getting increase ಅಂದಾಗ obviously V0 will also increase, V0 ಕೂಡ ಏನಾಗತ್ತಾ increase ಆಗತ್ತಾ. Okay, during negative half cycle, similarly during negative half cycle of the AC signal, during negative half the AC signal, forward bias across the emitter to base junction is decreased. This forward bias is decreased, therefore collector current also will decrease, because we know that the in case of C configuration, the current amplification factor is given by IC is nothing but it is equal to beta times IB. Remember, beta will be always greater than 1, and IC is completely depend upon IB. So during the forward half cycle, during the positive half cycle, more IB will flow. More IB flow agatappa andra, obviously if IB is larger, IC also will be larger. Since IC is larger, V0 also will be larger. During negative half cycle, so IB will be small. So since IB is getting small, IC also will be small. Andaga voltage output also will be small only. During negative half cycle, you will be getting a small voltage across the RC as an output. That's why you are getting a signal like this. Remember, there is no negative cycle here. The shape it looks like this, the shape will look like this, but these all values are positive only. Remember, these all values are positive only. Here you will be getting the positive and negative values, but here you will be getting only the positive values with a larger magnitude. The input voltage Vin, this Vin is given by IB into RB, because current IB is flowing here. You can show a resistor also here. So notes ನಲ್ಲಿ ಕೊಟ್ಟಿರ್ತೀನಿ ಅದನ್ನ. So this Vin is nothing but IB into this resistor is referred as RB. IB into RB is nothing but Vin, and output voltage Vout is nothing but IC into RC. Therefore voltage gain ಅಂದ್ರೆ ಏನು? Output voltage divided by input voltage, that is IC RC divided by IB RB. But we know that the current amplification factor beta for C configuration is defined as IC divided by IB. And if you rewrite the equation once again, you will be getting beta times Vout divided by Vin is nothing but beta times RC divided by RB. And if you write Vout will be equal to beta times RC divided by RB into Vin. In the sense, Vout will be always larger than Vin, because beta value it will be always greater than 1. Typically it ranges from 2 to 500, so that you will be getting always an voltage magnitude, output voltage magnitude greater than the input voltage magnitude. Next one is the thermal runaway. So this is a process which is unavoidable process anta helbodu. Typically this process is observed in the power transistors, so which will be used in the industrial applications, not in the normal transistors. Remember, so the output current IC is always dependent upon two factors. So as we know that the IC will be alpha times IE in the sense some portions of the IE plus a reverse saturation current, that is ICBO. So as we discussed in the first chapter, so here among these three factors, the ICBO, that is reverse saturation current, is temperature dependent. So what is this reverse saturation current? So whenever we operate the diode or semiconductor in reverse bias fashion, a small current will flow. Initially a small current will flow. This current ಈ ಕರೆಂಟಿಗೆ ನಾವು ಏನಂತ ಕರಿಬೇಕಾಗತ್ತಾ? reverse saturation current ಅಂತ ಕರಿಬೇಕಾಗತ್ತಾ, and this is due to minority charge carriers. This current is totally dependent upon the temperature. So there is a direct relation between the ICBO and temperature. How ಅಂತ ನೋಡೋದಾದಾಗ, with 1 degree Celsius rise in temperature, per degree Celsius rise in temperature, the ICBO almost doubles. ಇಲ್ಲಿ ನೋಡ್ರಿ, let's say this is at a temperature, let's say 10 degree Celsius ಅಂತ ತಗೊಳ್ರಿ. So ICBO increases, let's say this is at the 20 degree, it almost doubles the saturation, reverse saturation current here. The current value is almost doubled. Okay, so as in reverse saturation, in reverse bias condition, so in the collector to base junction, whenever it is reverse bias, So as we apply more and more reverse voltage, the temperature is going to rise. As the temperature rises, so as the temperature rises, this ICV also rises. Since the ICV is getting raised, IC, that is output current, collector current, it will also rise. So with the increase in IC, again temperature rises. With increase in the temperature, again ICV again rises, which corresponds to an increase in the IC again. This is a cumulative process. This is a cumulative process. So all of a sudden, within a short span of time, temperature across the junction increases suddenly, and it is going to destruct the transistor permanently. This process is known as thermal runaway, or you can simply define it as the process of transistor destruction due to increase in the temperature is called as thermal runaway. So how to this phenomena is observed, or this process is observed normally in the power transistors, not in the normal transistors. Power transistors in the sense those transistors which are meant to meant to be used in the power applications. Okay, how to avoid this thermal runaway, how to avoid the destruction of a transistor? So we should use some system called as heat sink. So we'll see it here, heat sink. So the purpose of heat sink is to um, remove the heat from the transistor and dissipate it into surrounding air efficiently. So whenever heat is produced due to thermal runaway, that heat will be dissipated into surrounding air, so that the transistor surface will be cooled down. So how the heat sink is constructed ಅಂತ ನೋಡಿದ್ರೆ, or what is it is made up ಅಂತ ನೋಡೋದಾದ್ರೆ, so heat sinks are generally made up of uh, metal foil, maybe aluminum foil use ಮಾಡಿರ್ತಾರೆ, and this is painted with black color. So black color in the paint ಮಾಡಿರ್ತಾರೆ. The another important feature that we expect from the heat sink is it should provide a large surface area. So if it provides a large surface area, it can dissipate the heat efficiently. And here one should insert a mica sheet. A mica sheet is inserted between the, let's say this is a transistor layer and this is the heat sink layer. In between these two layers, a mica sheet is inserted. The purpose of using this mica sheet, as you know that the mica is nothing but an insulator, and this is going to provide an isolation. This provides an isolation between the heat sink and transistor. So idu nimdu heat sink irutta, idu transistor irutta. This provide an electrical isolation. So if you don't use mica sheet, there is a chance of getting short circuit. So to avoid the short circuit, or to provide an electrical isolation between the transistor surface as well as the heat sink, we use a mica sheet in between these two. Okay, so this question will be asked for 5 marks in our examination. Next, these are the we will be dealing with the relationship between the current amplification factors in different configurations, that is alpha and beta as well as gamma. So alpha is these are very simple. I hope you can study them. I is given by IC plus IB, and beta is nothing but this is the current amplification factor in C configuration, and alpha is nothing but the current amplification factor in CB configuration. If you deduce the relationship between alpha and beta, alpha can be expressed as beta divided by beta plus 1, and beta can be expressed as alpha divided by alpha minus 1. Similarly, you can deduce the relationship between the gamma in terms of alpha as well as the gamma in terms of it can be represented in terms of alpha as well as it can be represented in terms of beta. That is given in the notes, so please read that one also. Thank you.